Gases are, what's something gases can do that solids and liquids cannot? Yes, they can be compressed. Gases are compressible. Because gases are mostly empty space. Therefore, they compress easily. If you put a gas in a container, what do they do to it? They fill their containers completely. They do not settle to the bottom. Of the container like solids and liquids. Gases move through each other and they mix. This process is called diffusion. This leads to the thorough, such a weird word, that one, thorough mixing of gases forming a what type of thing? Homogeneous. Ooh, that's crazy. Mixture. What do gases exert? Pressure. This pressure is due to the gas particles frequently doing what to the walls of the container? Colliding with the walls of the container in which they are held. Pressure is equal to force over area. And you can see there's a little picture here. Every time they bash into the wall, there's an outward force. Gases do what when they are heated? They expand. That is when we keep the pressure constant. And that's because particles take up more space when they move faster. They will bash into the walls with more force. So in order for the pressure to remain the same, the volume must increase, because if we increase the pressure, if we increase the force, then P equals F over A. If we want that to stay the same, we must also increase the surface area, okay? Which means that the container needs to expand so that we have a larger surface for them to collide with. Yes? And so you can see here, we have temperature 1, temperature 2 is higher, temperature 1 is lower, and the pressure is the same here and here. This little doodad, it's like a movable lid. We call it a movable piston. Now let's say that instead of having a movable piston, we had a piston or we had a lid that could not move. If that is the case, if we keep the volume constant, what do gases do when they are heated? They exert more pressure. So you have two options. Either you keep the pressure constant and the volume changes, or you heat it and you keep the pressure, or you keep the volume the same and the pressure changes. More pressure. As the particles move faster, they collide with the walls with more energy and more force. Pressure 1 is higher. No, it's not. It's lower. Temperature 2 is higher, and the pressure is higher. Does all of this mostly just make sense? Like, if you think about it, that's one thing about gases that are nice, is that they just kind of, you're like, well, if I kept the lid on it, the particles are moving faster, pressure is going to increase, because it just kind of, it seems to make sense. Okay, so that's 13.1 done. 13.2, moving right along. Kinetic molecular theory explains why gases behave as they do. The postulates. What the hell is a postulate? A postulate is a main concept. Okay? Gases consist of very small particles, each of which has mass and which are in constant random motion. The distances separating gas molecules are very large. The volume of the gas molecules themselves is very small compared to the large volume in which the gas is contained. Attractive and repulsive forces between gas molecules are negligible. Or you could say insignificant. Why is that? They're so far apart. Now, all the gases that we're talking about right now are ideal gases. Those, like, so if you're talking about a gas and it follows all of, like, Boyle's law, Charles' law, Avogadro's law, if it follows all of those laws absolutely perfectly, then it follows these things. In other words, the attractive forces are negligible. The volume of the gas particles is negligible compared to the volume of the container. The moment you start squishing the container so the particles have to get much, much closer to each other, then the IMFs might start to become non-negligible. They might become significant. Does that make sense? Okay. And if you have very, very, and if you squish it and the volume becomes smaller and smaller and smaller. All of a sudden, that small volume occupied by the gases becomes larger proportionally compared to the overall volume. Okay, so what we're dealing with here, we call those ideal gases, and we can use all those beautiful rules just perfectly with most gases. And most gases at room temperature and pressure behave somewhat ideally. Okay, we can say they have no volume, the particles take up no volume, and there are no intermolecular forces between them. Okay, so we just ignore the fact that they actually take up a tiny bit of space, and we ignore any random IMFs that might occur. Collisions between gas molecules are perfectly elastic. And an elastic collision is one in which no energy is lost. In reality, collisions are sometimes non-elastic, which means they do lose a little bit of energy when things collide. But again, this is an ideal gas, so gas molecules may transfer kinetic energy to one another when they collide, but no kinetic energy is lost into, I guess I was going to say no kinetic energy is lost in turning into, I don't know what I was actually thinking here, turning into other forms of energy. I'm sure there's a better way of phrasing that, but you get the idea? Yes, okay. The average kinetic energy of the gas molecules depends on the temperature. Define temperature for your neighbor. Temperature is a measure of the average kinetic energy of the particles. So if we have a higher temperature, we have greater kinetic energy. If we have lower temperature, we have smaller kinetic energy. You can check out these videos if you want to. We're not gonna watch them together because I think they're pretty straightforward. Pressure and barometers and manometers. So we are now on page 5. The pressure of a gas is the force it exerts on a unit of area. What's wrong with this pen? Am I turning it the wrong way? Yes, I'm turning it the wrong way. There we go. Area. Mathematically, P is equal to F over A, where P stands for pressure, F stands for force, and A stands for area. Did you guys learn all of these units of pressure over the winter break? Atmospheres, kilopascals, torr, millimeters mercury? Yes? Okay. Just so you know, our AP, not that one. Where is it? AP equation sheet. Let's see what they give you here, because it's a little bit different than in the past. Oh, no, I don't want that one. I want that one. There we go. Okay. Do they not? Oh, they don't give you any of the other ones. So I guess what that means is that they will only be giving you atmospheres, because they've not given you conversions to torr and millimeters mercury. So they can't expect you to do the conversion if they're not giving you the conversion factor. That's brand new. Okay? So I think you guys can still do conversions because it's not a big deal. But yeah, you won't have to for AP because they don't give you that conversion anymore. Let's just check. Huh? Unless they do up here. They do. Oh, yeah, there it is. Okay, so it is in the unit conversion. So yes, you can do things in millimeters mercury and torr. By the way, if you're taking an AP exam this year, you probably already know this, but your data sheets are going to be on the computer.
Oh my gosh.
On the same, like, so you're going to have to kind of like,
Switch tabs?
Yeah. Including the periodic table.
What? Why do they do that?
Because they want to save money, because they have to print them out and send them out and all that stuff. And they're a money-making proposition, so there we are. I think they should just get the schools to print them out and be like, yeah, if you want to print it out, you can print it out. But no, apparently not. Crazy. Okay, anywho, just so you're aware, one atmosphere has, it's an exact number, okay, when it's in that conversion factor. 760 torr has 3 sig figs because it's not to the tens position, it's to the ones position. 760 millimeters mercury has 3 sig figs. And 101.3 kilopascals has 4 sig figs. Where is this the pressure? This is the atmospheric pressure at sea level. So Vancouver has pressure very close to pressure at sea level because we're close to the sea. This occurs, yes? How is the what? Because I'm telling you that it is. It's not uncertain in the tens position. It is uncertain in the ones position. Make sure you write 3 sig figs. I'm just telling you. Okay? Occurs because air has, what causes atmospheric pressure? Air has mass, and it is attracted by Earth's gravity. So it is literally the amount of force exerted by the column of air that exists over top of an area. P equals F over A. And here's a picture below. Okay, so here is our sea level, and all of these particles contribute to the weight, the pressure at this altitude. If you go higher up, right, like say you were on top of a mountain, there would be less pressure because there's less air on top of you. Atmospheric pressure is how much at sea level? 1 atmosphere. What happens to atmospheric pressure as you move higher? Atmospheric pressure decreases as you move to higher elevations because the mass, STP and what? Yes. The column of air is shorter as you go up, so it contains fewer particles. Therefore, if you have fewer particles, you have less mass, you have less force, you have less pressure. Here is a barometer. Most barometers don't look like this because having open dishes of mercury lying around is not a very safe practice, but they all work in this general way. We have the air pressure from the atmosphere pushing down on the mercury. And when it presses down on the mercury, it pushes the mercury up into the glass tube. Barometer for measuring atmospheric.
Why can't you use water? Because like
Because you would need a tube that was much taller and skinnier. Is that right? Yes, you would need, actually, it wouldn't have to be skinnier, but it would have to be taller because water changes a lot more. Mercury gives you something reasonable that you can work with. Okay. So what they do is they take a glass tube and they get rid of the air. They use a vacuum to get rid of the air and they put it into a dish full of mercury. The air, the atmosphere, presses down on the dish and it forces some of the mercury up into the glass tube. An increase in pressure forces the mercury to rise inside the tube. Now, each of these little markings on here, 1 millimeter markings. Okay, so each of these is 1 millimeter. So literally, if we started here, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This would be 14 millimeters of mercury. That's literally what millimeters mercury means. It means it will go 14 millimeters up the tube. Okay. As pressure drops, mercury leaves the tube, decreasing the height of the column. So here we have the pressure exerted by the atmosphere. This is a bit nicer of a picture. Pressure exerted by the atmosphere and the pressure exerted by the mercury column on the mercury surface. So we have the atmosphere on the mercury surface and we have the mercury column on the mercury surface, and those two are equal. So let's say that this height was, oh, here we go. If the barometer at the right were at sea level, what would height be in centimeters? Hmm? 76.0 centimeters, because at sea level, pressure atmospheric is equal to 760 millimeters of mercury. And so it would be 76.0 centimeters tall. Does that make sense? So those are barometers. That's how they work. They literally measure the millimeters of mercury. They literally measure pressure. What? I don't know what I'm trying to say in this sentence. They literally measure the height of the column of mercury in millimeters of mercury. There's a line in there for some reason that I don't understand. Sorry about that. Some books use inches of mercury if they're published in the States. Oh yeah, I know. Manometers. These are something you might actually come across in the AP exam. I have seen manometer questions. And a manometer is similar to a barometer, except that it is a device used to measure pressure of contained gases. Now, these are two open ends. This is a manometer with two open ends, and we have it filled with a liquid. And because the only pressure exerting on it is atmospheric pressure, the levels are going to be the same, okay? Now, we can have a one open-ended manometer where we have this end is open, and the pressure pushing down is the atmospheric pressure. And then in the part on the left, we have a sample of a gas, okay, in here. Is it pushing with the same pressure as the atmosphere or a different pressure? A different pressure. Is it pushing with more or less pressure than the atmosphere? It's pushing with more pressure, okay? So the pressure of the gas is greater than the pressure of the atmosphere. How much greater? And let's assume that this is, just use a letter for me. H. Okay, so the pressure of the gas in this case as long as these were both in millimeters mercury.
H just also.
Okay, if it wasn't in millimeters mercury, like if you wanted to do it in atmospheres, you would have to, like, let's say this was mercury, you would have to convert millimeters mercury that you measured here into atmospheres, say, if you wanted to do it in atmospheres. So your units have to be the same. But if you're just using H, then put your pressure in millimeters mercury as well, okay? And that's going to be equal to the pressure of the, nope, that's wrong. There we go. Is that better? Yeah. How about here? Is the pressure of the gas greater or less than the pressure of the atmosphere? It is less than, because the atmospheric pressure is pressing more. So the pressure of the gas plus H is equal to the pressure of the atmosphere. Is good? So here's a couple of examples. In this case, the gas is exerting more or less pressure. Our gas sample. Is the gas exerting more or less pressure than the atmosphere? More. Since it is pushing the mercury further down. We can now say how much more? Okay, how much more? Well, we are given a value for H1. we are told that it is 50.6 millimeters. We are given a value of H2, which is 77.8 millimeters. So what is the, how do we calculate how much more? We find the difference between them. So you would say, okay, what is the difference? 77.8 minus 50.6. Don't forget to put your units in there. If that happens and you guys want to answer the phone, you can just say, hello, Miss Spence's room. Because it's kind of far over there. And I can't plug it in here because otherwise I can't plug in my internet because it won't split properly, which is really irritating. Anywho, 77.8 minus 50.6. Oh, I can do this in my head. So this is going to be a 2 here and 17.2. Is that correct? 27.2? 27.2. Millimeters mercury. So what is our gas pressure? It must be the pressure of the atmosphere plus 27.2 millimeters mercury. So what is our pressure of the atmosphere? You'll be told what it is. Okay, this one happens to be at sea level. 760.0 plus 27.2 millimeters mercury. And that is equal to 700 and, nope, 837? Is it? No, 787. I just can't do math this morning. I don't know. Is that good? Okay, good. Phew. Good thing you guys are here. Can you guys do the next one on your own? It's got a conversion in it.
Oh my God. Wait, I have to change this. Doesn't matter which way. Oh, the
Did I add them? Oh, I probably did. Look at me. Yep. 117.8 minus 67.5. Thank you. 50.3. That looks better. Huh? Yes, I added by mistake. That's what we're correcting right now. 50.3 sounds better?
Yeah.
Good. Okay, good. Good. Yes, you're supposed to subtract. Like I said, it's a good thing you guys are here because I don't know what I'd be doing this morning.
Like, how about, should we do like H2 minus H1, which is like 50.3?
You can and then just add, yeah. Either way is fine, whichever, as long as you're making it bigger or making it smaller appropriately, you're good to go. Now, if you've forgotten, it's 101.3 kilopascals for every 760 millimeters mercury. Yes? Oh, I don't know. Let's see what they give you here. Yeah, I guess it's only 3. Let's put it back to 3.
Where do you get 748.4?
I got 748.4. Is that what you got? Oh, let me try it again. 99.75 times 760 divided by 101.3 equals 748.4? No? That's just the atmospheric pressure. We're not done yet, right? Because we now need to say 748.4 minus 50.3 millimeters mercury. And that gives us 698.1. Is good? Whoop. Yeah? And then you guys could try a few of the practice problems on 13.1D and we'll be done for the day. Yes? Don't put your book away. Try a few of the practice problems. And then we can move on next day to gas laws. That'll be on Thursday. Yes. 11 to 12. Okay? Did I do something wrong? Yes. Yes. Yeah. We did. Did you change? Did you decide you wanted to go at 10:30?
No, I guess I have something at 11:30.
Oh, you have something at 11:30?
But it's fine.
We can change it back. Can we make it at 10:30?
I was looking at 12. All right.
Because we got someone with a conflict.
Like, I'm their school day.
Pardon me? You have a bio thing? You're sure it's not at 12:30?